Hello everyone, my name is Meng Yue. Thank you for the interest in this panel session. So in today's presentation, I'm going to discuss an enhanced probabilistic continuous analysis tool or ePCA tool for assessing renewable impacts. So the objective of this study is to develop an enhanced PCA tool. We want to better account for various uncertainties. So the major features of these ePCA tools include: first is a built-in repository for outage data and statistics, and it can be used for Monte Carlo simulation. The second one is the investigation of renewable intermittency impacts. This kind of impacts on the continuous analysis has not been investigated yet. And third one is we implemented a so-called well-being approach. The last one is we developed improved quantification module in the ePCA. So essentially, ePCA is a set of Python scripts developed to incorporate all of these features and external to the PSSE, but it is used to drive the PSSE and to take the advantage of the built-in probabilistic continuous analysis capability inside PSSE. The first issue we addressed is so-called data pullability. So currently, in order to get the outage statistics such as outage frequencies and duration time, so what we do is we first collect outage data from different sources. Then we simply lump all of them together. If we want the outage frequency and duration time, we just take an average or the arithmetic means. And the question we wanted to ask is, are the failure rates in different areas the same or not? So in order to determine this, we introduced a form of statistical testing, chi-square test, to determine whether we can pull all the data together. The conclusion was we could not put all the data together. It depends. One of the obvious reasons is, for example, environmental conditions will have different impacts on the transmission outage frequencies, and different utility companies have different maintenance schedule which will affect the outage duration time. So that's why not all the data can be pullable. This is why we introduce this so-called population variability to model this kind of outage parameters. So this is a sample outage data repository for non-pullable transmission components. Components here are the AC circuits of different voltage levels. So what we do here, we have frequency, we have duration time of the outages, and we are trying to use a log normal distribution to model them with the parameters developed from the historical outage data. Then you can look at the arithmetic mean and the true mean value, the variance, 5th percentile, 95th percentile. And basically this distribution you can use to describe the outage rate and frequency from different data sources. The second issue we investigated, this is a major issue, is about the renewable intermittency on the continuous analysis. It has not been investigated before. So the motivation for having these studies, if you look at historical wind generation data, very often you can observe fast ramping events. That means the wind generation may go down significantly within a short time period. For example, 10-20 minutes, the generation can go down significantly. And this kind of ramping events apparently has the same impact as the generator outages, right? So generator outage, you will have loss of generation goes down. And here a ramping down event will cause the wind generation to go down quickly. This is why we are trying to model this kind of ramping events as outage. We call these intermittency induced outage or IIOs. And of course, a bigger concern is multiple wind farms. If they are located together, you may observe the fast ramping events simultaneously in the multiple wind farms. You look at the right figure here, 3 wind farms, fast ramping events almost simultaneously here. And after that, it goes back to a previous generation level. So this kind of concurrent ramping events we call it common mode outages. It apparently has a bigger impact on the system. This is why we are trying to model them. So in traditional outage model, the component is either down, up, or down. And here, because the intermittency, it might cause generation to drop to different levels. So you might have multiple outage modes for wind generation. That's why in the right figure you have these states of down 1, down 2, down 3, all the way to down M, representing the generation drops to different level. So after having this model, the rest is to develop parameters, outage frequency, the duration time for this kind of events. Again, we extract this kind of fast ramping events for historical data to develop this kind of parameter. One thing I want to emphasize, when we are developing parameters for common mode outages, one parameter we need to pay attention is this correlation between these different wind farms. So theoretically, different wind farms, they are highly correlated. You can observe more frequent concurrent ramping events or common mode outages here. Look at this table, it gives you the frequency for different for wind farm with different correlations. So this kind of model and parameterization will provide a framework. We can incorporate this kind of model into the PCA framework now. So other features in PCA, because we have distribution for components, we can use Monte Carlo scheme. We take samples of the outage frequency and duration time and calculate the distribution of system problem indices. And we implemented this so-called well-being approach, and also for better quantification, we developed this so-called binary decision diagram-based method to quantify the exact probability and the frequency and the duration time of the system problems in PCA. So we are going to show a case study here. So for PSSE PCA, we need a standard case file such as a continuous list outage statistics. That's the same file we need here for ePCA. Since we are considering IIO and CMO, we will need wind farm continuous files for the ePCA, and also we need the statistics for the IIOs and the CMOs here. The basic case study, the base case is based on this WAC system. Of course, it has wind generation, but we don't know how much wind they have. So that's why we build 3 cases here. Case 1, assume we have 10% more wind generation than the base case, but we don't consider IIO and CMOs. The second one is we have 10% more wind generation compared to the base case, but we are considering IIOs and CMOs. Third one is we have 30% more wind generation, and we also consider IIOs and CMOs. The results here are fairly clear. If you look at this table, you can get this conclusion very quickly. If we include renewable generation, IIOs and CMOs, you will notice that system problem frequency goes up, but the duration time goes down. This is the case for overvoltage, undervoltage, and overall system problems. And if you include IIOs, this will happen. If you have more wind generation, this is more obvious. And the reason is fairly simple. The intermittencies in the wind farm generation is much more frequent compared with generator outages, right? And at the same time, the duration time of this intermittency is much shorter compared to the generator outage time. This is why we have this kind of observation here. So in this study, and this ePCA2, we have built-in reliability data repository. We resolve this pullability issue, and we also model the fast ramping events as IIOs, outages, IIOs and CMOs. So we have this probabilistic model that can be incorporated into the current PCA framework. We implement the well-being, and also we perform case study to confirm the impacts of the data pullability issue and also IIOs and CMOs on the continuous analysis. In the future, we will continuously update the reliability data repository we will also consider intermittency impact associated with solar PV. In this study, we only consider the wind. We will continuously refine the ePCA. The one feature is we are working on this multi-value decision diagram. It's an improvement of the BDD, because for the wind farm outage, wind farm may have multiple outage modes. It's not up and down. That's why we need this MDD, multi-value decision diagram. And also we will develop graphic user interface for ePCA. Many thanks to ERCAT, including Dr. Sangwook, Julia and Julia for providing wind generation data and technical support. And also many thanks to Dr. Milorad Pepik for providing system data and utility perspective. At last, many thanks to Dr. Ali Gassemian, the program manager of Advanced Grid Modeling Programming Office of Electricity, for providing the project funding. This is all. Thank you for the interest.